Practically every man-made object in modern times starts its life as a parametric CAD design. The ubiquity of these tools in the design process means that any assistance rendered by machine learning can have a massive impact on supporting design and understanding of the objects in our world. The challenge, however, is CAD geometry has a unique format, the parametric boundary representation. Further, while this format is used for a variety of different tasks in industry, task-labeled datasets in this format are typically proprietary and expensive to reproduce. Fortunately, there is a copious amount of unlabeled CAD data, so we ask, can we leverage this data to support learning on small labeled collections? The answer is yes, and we achieve this with a novel geometric self-supervision task, learning to rasterize CAD models with a new hybrid implicit-explicit representation. This task enables us to learn a novel representation that understands CAD. We show that this representation can be used in a variety of tasks, showing great improvement in low data regime and state-of-the-art results in non-sparse settings, despite using very lightweight prediction networks. Parametric CAD models are constructed as a sequence of operations that build the geometry bottom up, essentially creating a program. They are then exported into the BREP format, which describes the geometry as a set of vertices, faces, and edges. Of course, one can convert them into more classic geometric formats, but the BREP are the preferred form in engineering because they represent geometric features in infinite resolutions, allowing a vast set of design and manufacturing tasks, from assembly and motion design to material and manufacturing specification and visualization. Unfortunately, it's very hard to find large labeled datasets for such tasks, since this information is typically proprietary, so our goal is to leverage information from unlabeled datasets. To do that, let's sit back and see what's so hard about the BREP format. BREPs represent shapes as networks of smooth surface patches called faces, each of which is defined by a parametric equation such as planes, cylinders, spheres, cones, and tori. Importantly, these equations have no notion of boundaries. To address this, BREPs define edges which come together in closed loops to bound the faces. Like the face's parametric surfaces, edge geometry is defined by parametric curves, which again have no notion of boundary. Finally, the vertex is introduced to bound the edges. These are parameterized by spatial points and so need no bounds. Faces, edges, and vertices make up the BREP's topology and can be thought of as a topological graph, where links encode an is-boundary of relationship. As you can see, the BREP form was designed to be compact, have infinite resolution, and allow easy referencing and editing. It was not designed to enable easy visualization or straightforward geometric interpretation. This is our fundamental insight. In normal CAD workflows, it is the job of a CAD modeling kernel, a monolithic piece of software, to interpret these BREP structures through sophisticated algorithms that enable rendering. So, inspired by this fundamental insight, we asked, can we learn to do this geometric interpretation, and can this help us be able to work better with BREPs? We want to learn to interpret BREP geometry, so what representation we learn to interpret into? A face in a BREP is represented by an explicit parametric surface that has no boundary, and a graph of adjacency relationships to parametric curves and vertices, which bound the surface and create the face. We realize that this graph is defining an implicit shape on the surface. Both the explicit surface function and the implicit face shape share the same parameterization domain, so we can combine them into a novel hybrid implicit-explicit representation. We train a neural network that, given a latent encoding of a BREP face and surface coordinate inputs uv, jointly decodes the position of those coordinates in R3 and the signed distance on the surface to the face boundaries in R. These latent codes are computed with a graph neural network encoder. If our target is to decode a bounded surface, we need an encoder that can capture all of the pertinent information about a surface as well as its boundary. The main observation we make here is that a face only needs to know about its adjacent edges to know where its surface is bounded, and similarly, an edge only needs to know about its adjacent vertices to know where its curve is bounded. Based on this, we use a hierarchical graph neural network to encode faces. Our network has two sequential and directional message passing steps, implemented as multi-headed graph attention layers, from vertices to edges, and then from edges to faces. Now that we have encodings of BREP faces, we will use them to learn new task-specific decoders for useful problems from very little data. These task-specific networks are very small and lightweight, do no fine-tuning of the encoder, and do not require the sophisticated algorithms from CAD kernel software for training or inference. We trained our encoder-decoder network end-to-end over 23,000 BREPs from the Fusion 360 Gallery dataset. Here are some examples of rasterized results and unseen examples using this encoder. While there are definitely artifacts compared to the original BREPs, there is enough encoded detail to enable downstream tasks. To illustrate this, we experimented with the decoder with different benchmark tasks. In doing so, we compare our method to prior work on deep learning on BREPs. The first task is segmenting a model based on which constructive operations, like extrude or fillet, was used to create each face. We trained many instances of our network and several baselines from the literature using successively smaller training sets. We repeated the experiments multiple times and indicate here both how accurate and how robust our method is. Compared to existing methods, our technique achieves significant performance improvements in the few shot regime and also produces more consistent results. Notice that the results with only 100 examples, our model is able to pick out several of the operation types, whereas most of the baselines have only learned the dataset average. Looking back at this plot, we also notice that our method further achieves state-of-the-art results at top data sizes, which is impressive given that the other baselines are actually much larger networks, trained end-to-end with access to CAD kernel processes. As seen in this plot, our method is orders of magnitude faster to train than prior networks, which is critical if we envision using this to train few-shot CAD tools on the fly. I'd also like to highlight this green curve, which is the only prior self-supervised BREP learning approach and uses contrastive learning. The striking dissimilarity in performance emphasizes the efficacy of our geometry-based self-supervision. We also experimented with segmentation based on manufacturing operation, using a benchmark that mostly consists of cuboids with various planar features cut into them. Even though this data is out of distribution considering our training set, we're able to generalize. The plot showing various training set sizes shows that our method is more robust than end-to-end baselines and outperforms it in few-shot regime, as well as tying state-of-the-art over the full dataset. This positive result, despite the disparity between our pre-training dataset and task dataset, shows that the encodings we learn are indeed general and robust to drastic changes in the kind of geometry. Finally, we tested our approach on part-level classification, condensing our per-phase codes into a single vector. This benchmark is a classification into categories such as brackets and gears, and has many instances of variations of a few base models. Since these tend to be easy to classify for networks with geometric understanding, we also see a small margin for improvement. Still, our method outgeneralizes both baselines at low data sizes, as well as achieving perfect classification on the test set given the full data set. In summary, in this work we enable for the first time learners to support the vast array of CAD tasks for which labeled data is sparsely available. We experimented with 3 CAD tasks for which large-scale data is available to validate our method, and its success convinces us that it will be broadly applicable to the CAD applications for which data is rare. CAD models comprise the vast majority of manufactured models in our everyday lives, and we believe that enabling learning on these collections with a representation that requires less data can enable exciting directions both in better understanding our world, recovering material, manufacturability, and functionality information, and in support for modeling and editing applications. Additionally, our method enables a fully differentiable embedding of BREP geometry compared to prior work that required non-differentiable CAD kernels, paving the way for exciting future work on CAD optimization and reverse engineering.